Then we take our slow pointer, leave it here. So our slow pointer is going to be here, right? And then we're going to be done. We know for sure that every single value in the array is going to be in the range 1 through 4. That means point here. So we can here, so we're going to go to 2 length of the cycle, right? In this case, it's 5 minus x, right? Because we're going to be starting at phase 1 of this algorithm. We're going to have 2 pointers, fast and slow. They're always going to start at 0, remember, because we know 0 is not a part of the cycle. That's for sure. And we're going to keep iterating through these loops. I think there's an easier way to write this code, but I'm lazy. So just while true, we're going to, and we start out with while true because we want to keep going until they intersect. But notice how they already intersect at the beginning. So we're going to update slow. So basically slow is going to be set to whatever it points at. So nums of slow, right? And then fast is going to be the opposite, or the same thing, nums of fast. But remember, we're advancing fast twice, and so we can just do this. And of course, fast and slow are always going to be in bounds, right? They're never going to point out of bounds. We know that for sure based on the restrictions that we're given. And if slow is equal to fast, that's when we can break out of the loop. If they're not equal, then we're not going to break. This is basically a do while loop, but I don't think you can do that in Python. So once we've done this, that's how we know, okay, fast and slow intersected here. So now we're going to create a second slow pointer, slow 2. We're going to set it to the beginning, right, back at index 0. And now we're going to keep incrementing this slow pointer and the first slow pointer until they intersect. So this is phase 2 of the algorithm. While true, advance the slow pointer by 1. And advance the second slow pointer by 1 as well. Notice how trivial this code is. The hard part is just figuring it out. So, and we're going to keep going until they intersect. So if these were equal, then we can break out of this loop and then return the slow pointer, right? We can return either of them, slow 1 or slow 2. Index that they're at, right? Slow 1 and slow 2 are always an index, and the index that they're at is the duplicate number because we have multiple values pointing to the same value. That's the duplicate. We can actually take this and return it here. So I'm just going to go ahead and do that. And this is the entire solution. Okay, I don't know what I was thinking. I don't know why I put fast on the outside. This is nums of fast, which is a number, which is a different index. And then we're going to use that 1 positions. So in this array, we have 5 different elements, right? And we know that the elements are going to be in the range 1 through going to point. What does that tell us about our linked list? That means at the node that's labeled 2, each value of the node, each label is going to map to the index. So this is basically node 2, right? What that tells us about node 2 is that multiple nodes are going to be pointing to node 2, right? Therefore, we know that this is the one that's going to be the start of the cycle. We know for sure there's going to be a cycle, and we know for sure there's going to be a portion before the cycle. The portion before the cycle, of course, is eventually going to lead us to here, which is the start of the cycle. And of course, there's going to be another node that completes the cycle, right? Pointing back to this node. So if we can somehow identify the beginning of a cycle in this linked list, then we will know that that beginning of the cycle is the return value that we're looking for. In the output, you can see, yes, 2 is the duplicate. That's the one we want to return. Therefore, we want to return the start of the cycle. So at this point, it's all about applying Floyd's algorithm to find the beginning of a cycle. So that's, once you've determined that it's a linked list problem, then you just need to apply this algorithm. And this algorithm itself is actually also not very intuitive. So let's look at a slightly different example so I can illustrate the Floyd's algorithm. So first, I'm just going to tell you what the algorithm is, and then I'm going to explain a little bit of the intuition of why it actually works. So the slow pointer and fast pointer are both going to start at this position. The slow pointer, of course, is going to be shifted by 1 each iteration. So that's 1 jump, that's 2 jumps, that's 3 jumps. So we just made 3 jumps with our slow pointer. Let's do the exact same thing with our fast pointer. So remember, a jump with the fast pointer is going to be 2 positions. So that's 1 jump, that's 2 jumps. And let's make 2 more jumps from here. So we're going to go to 2 and then back to 3. So you can see that it got a little bit messy, but we made 3 jumps with the fast pointer and we made 3 jumps with the slow pointer. And you can see this is the first position that they intersected at. So this was the intersection of the 2 pointers, right? This was the first intersection. So that's the first phase of this algorithm. First, we find the first position that they intersect at. Then we take our slow pointer, leave it here. So our slow pointer is going to be here, right? And then we're going to be done with the fast pointer. We're going to take a second slow pointer and put it right at the beginning of the array. And each of these slow pointers, we're going to keep shifting them by 1 until they intersect 1 more time. So this slow pointer is going to be shifted by 1. This slow pointer is also going to be shifted by 1. Hey, we just found out that they intersected, right? And this second point of intersection is always going to be the result. It's not intuitive at all why this is the case yet, but let me explain that. But now you know the algorithm. If all you wanted to do was memorize it, that's literally it. Now you can code it up. That's why I don't like this problem, because it's simple if you've solved it before. So this algorithm relies on the fact that the intersection point, like the first intersection between the 2 pointers, the distance between this point and the beginning of the cycle, which in this case is 1, right, is always going to be the same as the starting point distance from the cycle, from the start of the cycle. That's also 1, right? Since we know that's the case, that's how we can take 2 slow pointers, start one here, and then keep shifting until they intersect. Then we get the result. But why is it the case that the distance between this is the same as the distance between this? Looking at this bigger example, why is it that the distance between the start and to the start of the cycle is always going to be the same between the intersection and the start of the cycle? Why is that the case? Well, let's just draw out a few distances. Let's say the distance, this is P, right? Basically, P is the number of previous nodes we have before the actual start of the cycle. And let's just say, arbitrarily, this is the intersection point between the 2 points, right? And we don't know that this is going to be the same, so let's just label it X for now. Let's not label it P, because we don't know for sure that it's going to be the same. Let's label it X. This is our unknown. And then the remaining portion of the cycle is going to be C, which is the length of the cycle, right? In this case, it's 5, minus x, right? Because the total cycle is 5, which is c, and this x portion makes up the remaining portion of the cycle. That's why this part is c minus x. So we know that the slope pointer is going to start at the beginning, it's going to traverse this p portion, and then it's going to traverse this c minus x portion, and it's going to land at the intersection point, right? Now we know that the fast pointer is going to do more than that. It's going to, of course, do this p portion once, then it's going to do a complete loop, right? Because remember, the fast pointer is going to outloop the slow pointer, and it's going to overlap the slow pointer. So it's going to have to complete a full, at least one full loop. And then once it does a full loop, it's going to be back here. And then it's going to traverse this c minus x portion to get to the intersection point, right? We don't know where the intersection is. Obviously, I drew it over here, but it could be anywhere. So let's write that mathematical equation out. So we know that 2 times the number of iterations the slow pointer does is equal to the number of iterations the fast pointer does, right? How many spaces it moves versus how many spaces the slow pointer moves. Of course, the fast one is twice as fast. That's why we have to multiply the slow one by 2 to make it equal to this one. And how many iterations did we say that the fast one does? It's going to do p plus cx, right, to get to this position. And then it's going to do another complete cycle starting from here to get back to this position, right? So the fast pointer is going to be p plus c minus x plus c again. So more simplified, it's going to be p plus 2c minus x. The slow pointer is just going to do p, and then it's just going to do c minus x. So we'll have a 2 on the outside, p plus c minus x. So I'm going to take this equation and simplify it over here to the right. So once we simplify it a little bit, we're going to get 2p plus